Okay, welcome to note set 16A, where we'll try to put some pieces together and look at the total solution for AX equal to B. And this is material covered in section 3.4 of the textbook. So we've been, kind of tiptoeing around all of this. And we're going to start seeing how all these ideas in chapter 3 start to fit together. So when we first started off, we were limiting ourselves to AX equal to B, where A was square and invertible, and there was just one solution, and we could find it by elimination. Then we expanded and said, well, what happens when A is not necessarily invertible or might not even be square? And we saw that we could still do things with elimination. We had to deal with some issues of when does B, which vectors B give us, actually give us a solution, and we had to deal with the fact that there might be multiple solutions, although we haven't really seen that all that much yet. But now we're getting to the all the machinery that allows us to very systematically handle AX equal to B under any scenario. Yep, okay, we got that. Don't show this message again. But I guess every time I reboot my computer, that comes back to, it forgets that I told it that. Anyway, here's an example. We've got an A matrix. We can do elimination. We get down to something that looks like this. That's our upper triangular matrix. And you can see that in this case, when we got to this step, we had two rows that were identical at the bottom, and so then after that last step of elimination, we end up with an entire row of zeros, and that's indicative of a situation that tells us that there's going to be some issues that we need to deal with. So looking at that last row, and that comes about, that last row after we've done the elimination, being all zeros, comes about because of something about the rank of this matrix. So rank, if you remember, we talked about it kind of measuring the true size of the system of equations defined by A. Well, A looks like there should be 3 equations, but in reality what we're seeing here is that there's really only 2 equations, that the third equation defined by A is redundant in this case. So we really only have 2 equations in 4 unknowns, and so that's the rank. And we one way we talked about getting the rank was by looking at the number of pivots. So here we have 2 pivots, so the rank of A is 2. And the other way that we talked about looking at the rank was by looking at the number of independent columns or the number of independent rows, and we said that would be exactly the same. So in this case, we might be able to see that these rows are linearly dependent with each other. In fact, if you look and notice that if you add the 2 top rows together, you get 3, you get 6, you get 8, you get 10. So the bottom row is nothing more than the top 2 rows added together, and so that shows that the bottom row is dependent on the top 2, and that is why we have a rank of 2. That's why we end up with 1 out of the 3 rows being 0, and the remaining 2 eliminating to something where each of those rows has a pivot in it. So we've got 2 pivot rows, 1 row of all zeros. Now, we also looked at doing the similar kind of elimination on the augmented matrix. So on the next slide, we'll augment our matrix to have the B's over here. So here's our A matrix put in there. If we do the same series of steps, we can identify our pivot columns and our free columns, which we could also do here. It's a little easier maybe to do it here. So we've got a pivot here, and we've got a pivot there. So our pivot columns are 1 and 3. Our free columns are 2 and 4. And notice that when we're all done, we end up with our 0 row at the bottom, which we knew was coming. And we have this new column on the far right. And the key thing to look at is all of this stuff down here. So that tells us that no matter what our solution is, whatever x is that we put into this, this x times all of these ends up giving 0, and that must be equal to b3 minus b2 minus b1. So in other words, that's the condition on B necessary for there to be a solution. So this thing that we extracted from the last row here tells us the condition that B must satisfy. So that tells us something about the column space that we'll talk about later. And we've already seen that AX equal to B is solvable when B is in the column space of A. And for our condition, or for this example, that condition we just found on the B's tells us the condition that B must satisfy to be in that column space. So it turns out to be a two-dimensional plane in this three-dimensional space. So it's basically just saying that if a linear combination of the rows of A gives a 0 row, then the same combination of entries of B must give 0. That's basically what it's saying. So let's suppose we were given a B vector that was a 1, 5, and 6, and you can go back and check to see that this does indeed satisfy that condition. And so there will be a solution, but the reality is that for this A, there will be lots of solutions. And in fact, we'll see later on, 1, why that's true, and 2, that it's not just lots of solutions. So lots of solutions is a little bit ambiguous. There will actually be infinitely many solutions, and we'll see that actually in this set of notes, but we'll see later an even more systematic way to look at this. So what we're going to do is, since there are infinitely many solutions to this, we'll find one. If we can find one particular solution, we'll see a way that we can parlay that one particular solution into all of the solutions, an understanding of what all of those solutions are. So here's how we'll find the one particular solution. So we've got pivot variables and we've got free variables. So to find the particular solution, we're going to set all of the free variables to 0. So set all free variables to 0. And so then we're leaving the pivot variables as variables. We plug that into AX equal to B and we solve for the pivot variables. So there's our system, and if we were to set the free variables to 0, so that's going to be the second and fourth one, that leaves x1 and x3. So we're going to set those to 0. So we're going to have x1 plus 2x3 will be equal to b1, but our b1 is equal to 1. So there's our first equation. Then we'll have 0 times x1 plus 2 times x3 is equal to b2 minus 2b1. And if you go look at what that is, you'll find out that it's equal to 3. So there's that. So we can immediately solve for x3 is equal to 3 halves, plug that in and figure out what x1 is. You'll find that it's negative 2. So there's our particular solution. And notice that we've got the x1 and x3, the pivot variables that we just solved for from these equations, and then we've got the two free variables that we set to 0. So there's our particular solution. So if you plug that in to AX, you plug that x into here, multiply A times XP, you will get B. So that's one solution to the equation. But we're saying that for this matrix A, there will be more than one solution. So how do we find those? How do we find all the solutions? That's what we're really trying to understand. Now remember, when A was square and invertible, things were nice. There was only one solution. But now we're looking at a more general case. So I've got one solution. How do I find other solutions? Well, here's the interesting thing. Suppose we know that there's some xn that's in the null space. So then we know that a times xn for anything that's in the null space will give us 0. So let's put anything in here that's in the null space. So it looks like we're just putting one vector in there, but imagine that it could be any one of the vectors in the null space. Once I put that in there, notice that when I distribute my a through, I'm going to have a times xp, which will give me b, and then I'll have a times xn, which will give me 0. So 0 plus b is equal to b. So that satisfies the equation as well. So not only does this work for just one vector in the null space, it works for each vector in the null space. So how do we capture that? Well, we talked about the null space matrix, or those special solutions to the homogeneous equation, ax equal to 0. We can use those. So we should extract our f. So here's our a. We went to u. Now remember, we need to go farther than that. We need to zero out everything above a pivot, and we need to normalize the pivot as well. So we end up getting something that looks like that. That's our reduced row echelon form. From there, we can extract our F matrix. So the F matrix consists of 2, minus 2, 0, and 2, but what we really want is the negative of that. So there it is. And then we interleave that in this case. We put this row in the row corresponding to the first pivot. We put the next row into the row corresponding to the second pivot. So there's our pivots. And then into the free variable positions, we put the rows of the identity matrix. That's how we found this n. This was the null space matrix. And each column was one of our special solutions. And we actually said that those columns will be linearly independent and they will span. In fact, there'll be a basis for the null space. So anything in the null space can be written as a linear combination of these two columns. So if we do that, and here, I don't think the textbook does this, but I've put brackets around this to show that this isn't if I just put it like this, that would just show, like, it would convey to you that it's a single thing. But by putting it in brackets, I'm trying to convey that it's a whole set of possible things. So we've got the one xp, didn't put that in the curly brackets. And then we've got all the xn's, the whole set of possible xn's. And so how do we write that? Well, there's our particular solution that we came up with. We take the columns from our null space matrix and put them there, and we put some arbitrary variables out in front. And so we now have a solution. Each solution to this equation will have this form for any particular choice of C and D. So we can set C and D each equal to 0, and we get our particular solution. But we can set C and D to anything, and we'll still have a solution to the equation. Because no matter what C and D are, anything created this way, when applied, when the A matrix is applied to that, will map to 0, because this is, for any combination, a vector in the null space. So now we have a whole space. Well, I'm not careful. I have to be careful there. We have a whole set of solutions. And let's take a look at them. So basically what we've done is we've found one particular solution here, which I'm showing as XP here. And, keep in mind that I'm showing 4 axes here. I'm trying desperately to draw R4 for this example, but we can't really draw R4. So you have to be a little bit clever, and have a little bit of well, you just have to bend your brain a little bit. We can't really show it, so we're just trying to convey or evoke it. So there's our particular solution. It's just one vector sticking up, out into our four-dimensional space. And then we had a plane. We said that the null space of A was two-dimensional, so it's going to be a plane in this four-dimensional space. And I'm showing it here as this little rectangle. Now remember, it goes on in all directions because it really is a space. And it also goes through the origin. And then what did we do? What we're doing to create any one solution to our equation, we're taking some vector in here. So suppose we take that vector and we add it to here. So it's going to be this. But we could take some other vector that lies in that plane and add it to that. So it's a little hard to see it over here. But let's do it this way. I now move that blue plane up and put it at the tip of my XP. And so now any vector that lies in this plane, so remember I'm talking about the solution coming from here up to some point, that will be a solution, that will be a solution. Anything that starts at the origin and goes up with its tip ending at that kind of elevated plane will be a solution. And that's the complete solution to the problem. It's a plane in this case. It does not go through the origin because it's quote-unquote elevated or displaced by our XP. So it's the null space plane displaced by XP. That's a good way to think about it. Now, if you can keep that in your mind, that will really serve you well in understanding how all of this machinery works. So here's an example, an exercise, and we're going to do a bunch of things for this system. So this is 3 equations and 4 unknowns. We're going to really wring this example out. So if you can follow through and do all of these things, you'll be in really good shape. So I'm going to, on this page, list everything that I want you to try to do in this exercise. Then you can pause the video, give it a shot, and then come back and I'll lead you through. I don't go through all the details, but I give you enough to kind of check your work. And if you're not getting it, then you need to go back and review some of the ideas that we've seen. So if we reduce our auxiliary system to UC, where U is upper triangular, we'd like to also find the condition on our B vector to have a solution. We'd like to be able to describe the column space. So in other words, in R3, what subspace, and I'm kind of giving it away here that it's a plane, but which plane must the B vector fall in order to guarantee that there is a solution. We'd like to describe the null space of A. So remember, that's in R4 because those will be the X vectors that will cause the AX to be equal to 0. We'd like to find a particular solution for a given B, and you should also kind of verify that given B lies in the column space. And then finally, reduce the upper triangular form to the R form, which is the reduced row echelon form. And from that, also figure out the special solutions, which will give you the null space matrix N, which will allow you to describe the null space of A in a different way. And then the vector that you get here, D, we'll see that you can use that to determine the particular solution. We didn't really talk about that, so if you can't get that, don't worry about it. Just come back and see how to do it. All right, so pause the video, give this a shot, come back, and we'll work it from there. All right, so hopefully you gave it a good try, and we'll now kind of lead you through this. Like I said, I won't go through all the details, but I'll give you enough insight so that you can kind of check your work and maybe get an idea as to what you should do. So the first thing we want to do is reduce our augmented system to an upper triangular system. So if you do some operations, row operations that we've been doing, you'll get something that looks like this. And so this is kind of the key step here. We start to see that we've got 2 pivots. So we've got 2 pivot rows. We've got 1 row of 0. So we're starting to see what our conditions are. We've got 2 pivot variables. We've got 2 free variables. We've got our reworking of our B vector. So that was the first step. Second part was to find the condition on the B's for AX equal B to have a solution. So the solution, we must have that this must be equal to 0 because of all the zeros. Now, if we had multiple 0 rows there, we would have 2 sets of conditions that the B's must satisfy. So that's what must be satisfied. So now let's talk about the column space. So which plane in R3 is the column space? Well, remember that this really is telling us that. And so our first way of looking at that doesn't use that, but rather says, well, the column space is the plane containing all combinations. Well, it's the space spanned by the columns of A. But what we can say is that if once we get to our form where we can identify the pivot columns, if we come over to the same locations in A, those locations will give us the columns that will span the column space. And so that's kind of key. So there are the 2 vectors that if we took all combinations of those would give the complete column space. So 2 vectors, linear combinations of 2 vectors in R3 will give us a 2-dimensional plane subspace in R3. Now another way to view that is every vector that lies in that space will have B values that satisfy this equation. Okay, question number 4. Describe the null space of A. In other words, find the special solutions of R4. So if you go back in a couple note sets ago and use those techniques, you can find that these are the special solutions. So how did I find those? Well, remember, we had this way of setting the free variables and then solving the equations. So what do I mean by setting the free variables? Well, for this step, for finding the special solutions, we set the free variables first. Each one of them is set to 1 while all the others are set to 0. So I've got 2 free variables. So for the first one, I'm setting the first free variable to 1 and the second free variable to 0. I put that into this system and solve it. And if you do that, you'll find out that x1 must be -2 and x3 must be 0. So you solve for the pivot variables. Then we go to the next one. So now we're going to set the first free variable to 0 and the second free variable to 1 and solve again. So we put that into this system and solve it, and we find out that we get -2 for the first pivot and -1 for the second pivot. So that's how we do it. Now, we've also seen in an earlier set of notes that we can do the same thing if we go to the reduced row echelon form. And then we can extract the F matrix, we can negate it, we can form our null space matrix N, and we can get the special solutions from that. And remember, the special solutions or the null space matrix, either one, the linear combinations of the special solutions, or equivalently, the linear combinations of the columns of N form the null space. So once we have those, this should be S, not X. For all C1 and C2, we form linear combinations C1S1 plus C2S2. Hopefully somebody else in my house will pick up that phone soon. There we go. Okay, so we'll continue on here. So now we have a characterization of the null space. Remember, that tells us what the space looks like. In this case, it'll be a plane in R4. Now we need to find the particular solution. Any particular solution. It doesn't have to be anyone that's special, but the way we do that is set all the free variables to 0. So that's just one way to do it because it makes it easy. So if you set all the free variables to 0, so our free variables are here and here, so we're going to be solving x1 plus 3x2 is equal to b1, and so on. So you'll end up with two equations that you can solve, and you'll find out that our xp ends up being minus 9030. And so now the complete solution is that particular solution plus all the vectors in the null space. And so this is just showing another way to find the null space and the particular solution for that matter. We haven't really talked about using the reduced row echelon form of the augmented system to find the particular solution, but we'll illustrate it here with this example. So we had UC, and we can take it farther to RD, where R is in the reduced row echelon form and D is whatever it ends up being. So if you do that, here's this. So we've got a pivot here. We've got a pivot here. So we need to zero that out. So if we do that, we'll get a 0 right there, but we'll still have a 2 here. And so, we have a 1 here to begin with, but if it were something other than 1, we would then have to normalize the pivots. And if you remember, we would form a diagonal matrix that has the reciprocals of all the pivots, and we'd multiply that through from the left, and that would normalize everything. And so then we end up with our with our R and a D. So here's the D. So if we went all the way here straight away, sound like I'm from England or something. If we went right to this form straight away, we would be able to see that we've got the 0 row at the bottom, which tells us that we've got just 2 equations that are really going on. We've got 2 pivots. We know that those are our pivot variables and our pivot columns, and we can extract from this. Let me clear some of this stuff off. We can extract our n vector, our n matrix directly from that. So remember, we find the stuff in the non-zero rows of the pivot columns, and that becomes our F matrix, which we then negate. So we have a -2, -2, and -1, and those go in the positions of the pivot columns. I think I just misspoke. We find the free columns here, not the pivot columns. So the free columns give us the F matrix. I guess that's probably why we picked the F name for that. So we find the non-zero row parts of the free columns, negate it, and shove each row into the positions of the pivot variables, and then stick the identity matrix rows into the free variable positions, and that's our N. And you'll see that that is exactly the same. Those columns are the special solutions that we got before. And then here's the really cool thing. We can come over here to this last column in the augmented form with the reduced row echelon form. We can extract those two, and we do the same kind of thing. They go into the positions of the pivot variables, and then the free variables are set to 0. Remember, our trick for finding the free variables, or finding the particular solution, was to set all the free variables to 0, and then solve for the pivot variables. So these things go into the pivot variable positions. And so now this is showing you the power of this reduced row echelon form. If you get it into the reduced row echelon form with the augmented, corresponding augmented vector at the right-hand side, you've got all the machinery you need to know to solve, to write down the complete solution to the system of equations. You can get the particular solution, just pick it right out. You can get the null space solutions. You can pick those right out, and you're ready to go. So that, remember, RREF is a MATLAB command, and so once it gives you this structure out, all you got to do is do some MATLAB indexing, and you can extract all these things and figure out what your possible solutions are, and that's powerful. So it's powerful theoretically, and it's powerful computationally as well. All right, so that's the end, and I'll see you in the next video.